Yes. Can everyone hear me? Very good. Okay. I'm not going to talk too much about what Hasting-Levitov models are exactly because it's quite complicated. So I'm just going to show some pictures and tell the general ideas and also the general idea of my results. Because that's kind of the thing. It's a nice area of math, right? A lot of pretty pictures, but a lot of the constructions are really technical, so they don't fit in 5 minutes. How do I start the full view? Control Alt, thanks. Very good. So yeah, the general motivation is this. We start with a unit disk because it's mathematically easy and we attach particles to it. In the simulation, they're all the same. They don't have to be the same. And we continue doing that. And as we do, we get the bigger and bigger cluster, a bigger particle aggregation. And the general question we want to answer is like, what would a scaling limit look like? So if I have like 1 million of these particles, what is a typical shape? With the idea that the size of the particle should go to 0 and become negligible. So the motivation is all kind of weird fractal growth processes. I think the original motivation was like how ash patterns form in chimneys because they do some weird things. But anyway, yeah, so there are two important questions, like how do we choose the next attachment point? So how do we choose where to add the next particle? Obviously, we want to do it random, but also obviously, depending on this choice, we might get different scaling limits. So two natural choices are either uniformly on the boundary. So I mean, the boundary has an area and I can just take that area, well, normalize such that the total area is 1. And then say that there's a probability measure that would give us an attachment point. Another one, which we've been looking into, is kind of if we start a random walk or a Brownian motion very, very far away, what's the first point we'd hit? So compared with the uniform measure on the boundary, we prefer more exposed areas. So if you have like something like this, the tips would have more weight, more likelihood than this area, for instance, which wouldn't be the case with the uniform measure. And the second important question is, of course, what kind of particles do we take? And the important thing, what I did in last year was kind of choosing IID particles. Because as far as I'm aware, the literature usually takes specific known particles. So for instance, disk, what I had in the beginning, or sticks, and only has the attachment point being random. Yes. So, and the other thing is, I'm looking at it from a continuous model side. So we can also take, for instance, a lattice and I work on a lattice. So the question is like, how do we even mathematically describe the model such that we can answer these questions? And the answer is to use the Riemann-Macklin theorem, which tells us that any two open domains in C that are simply connected, i.e. we don't have holes, have a conformal bijection, so bijective analytic function whose derivative never vanishes between those things. So then we always take the function from the exterior of the unit disk to the exterior of the unit disk plus my particle. And if I concatenate these functions, I get something that kind of particles that grow on a set. So this is how we do one particle, and we do several by just repeating this process iteratively. Which also has a nice thing that we can just choose the attachment manner by a measure on the disk in such a way that we get here what we want. So basically we do everything on this nice disk and then make sure that we get here what we want on the other side after applying this map. Yes, and I hope that I'm roughly in time. So the known results are kind of being both theorems. And this is a simulation by Amanda Turner, who used to work with my supervisor, who's still working on the project, but is now a lecturer or professor in Lancaster. And I've been generalizing this theorem that under a certain set of parameters, it converts to a ball that just gets bigger over time. And it also works if you choose reasonably nice random particles. So yeah. But there's also belief that there's a phase transition so that after specific value, you get a very different picture and something that's much more tree and much more fractal than this thing. Yeah. Thank you for your attention. Any questions?
Thank you.
Yes. So one of them is that the size of the particles go uniformly to 0 as as the number of particles goes towards infinity. which I mean is very natural because otherwise you kind of have something that stays in the scaling limit. If you look for a very weak result, and the other thing is I've kind of glossed over it because it's causing a lot of trouble. But when we do this iteratively, earlier particles are deformed by later particles. So if you don't undo this deformation and the particle size goes to 0, then we get a ball. And the particles, so there is a geometric quantity, which you call capacity, which is roughly kind of like a size, but not quite. You need some control on that. Yeah, that's basically it. But what we want to do next is kind of see how we can undo this distortion, or at least get something that in the limit behaves like if we hadn't had the distortion. But that's kind of technical and annoying, so.
Then let's thank Anna again.